Hello, I'm Heinz Hornung, owner and founder of Felicitas Customized Engineering, and I want today to introduce Felicitas PCBSim, our simulator, which we have nicely coupled to Cuts of the Eagle. And today I will demonstrate a standard circuit simulation. Felicitas PCBSim can also be used for signal integrity simulations, but today I will demonstrate a standard SPICE simulation. For that, I have prepared a small little circuit here, drawn in Cuts of the Eagle, with just a triangle generator on the top right-hand side, a very simple power supply with just a 9-volt block battery, and a start-stop logic with an SR flip-flop, 2 push buttons, and a MOSFET. Now, if I want to simulate that, the easiest way is just to export that schematic to Felicitas PCBSim, and for that we have integrated a small little button into Cuts of the Eagle. I will now start Felicitas PCBSim. Here we go. It is not yet very interesting because we have not yet loaded a circuit, but we will do so in a moment. So if I want to simulate that, I would at first just export that schematic to Felicitas PCBSim. And PCBSim is, well, of course, not immediately happy with that schematic because it is lacking quite some information for the integrated circuits. Well, this is not surprising because we need to assign a simulation model for each integrated circuit. Now with PCBSim it is very easy. I will demonstrate that. So we have here an analog devices operational amplifier as integrated circuit 1. So I right click on it and here's a context menu entry PCBSim, which I click on it right now, and this little dialog which opens is already stemming from PCBSim. So we have very nicely integrated that. It's not an Eagle dialog anymore, it's a PCBSim dialog. And this allows me to assign a simulation model to the integrated circuit. For that I select a model file, in this case a standard operational amplifier. And I choose a suitable component, in this case analog devices 823A. And now we have to assign the pins from the shape to the model. And this is easy because Felicitas PCBSim knows about pin names, so we can really use speaking names, positive supply, the negative supply, the non-inverting input, inverting input, and the output. That's it. So we have now already assigned a simulation model to the first integrated circuit. We are doing that same process again for the second one. I could make it a bit easier than that, but I will demonstrate it in this way again. So choose the right model and make the pin assignment, non-inverting input, inverting input, and output. Here we go. So we have already assigned both integrated circuits. Now we have here a little RS flip-flop, and this is a CMOS flip-flop. So I do again exactly the same. I call PCBSim, but this time I select a library digital, and this library has a number of digital primitives, and what I need here is a D flip-flop SR. And what we see is this model has a number of parameters. So it's a parameterized model. It's a general model for D flip-flops, and you can adjust the timing and the threshold voltages freely. Now we have a an ancient, very old CMOS part, so it is very slow. I say it had a delay from the input to the output of 100 nanoseconds. And I adjust the thresholds to approximately half of the input voltage, which is 4.5 volt. And output low might probably be 0.2 and output high might probably be 8.8 volt. And rise and fall times is in the order of magnitude of 50 nano. And again, I have to assign the pins here, which is an easy task. That's it. So we have now assigned all 3 integrated circuits. So I could have another go and just export that to PCBSim. Here we go. Now we don't have any error messages anymore, which is good. And on the left hand side, we see now a tree view of all the components which are in the simulation. So I could now hit the start button and see how it simulates, but I think we have forgotten something. If I go back to the schematic, we need the operation or the power supply voltage. For that, we have 2 possibilities. We can either add a voltage source to the schematic, or, well, a bit simpler is I do again a right mouse click on the battery with and open and call PCBSim, and PCBSim is now saying the component is excluded from the simulation, but we can use change type in order to assign it a simulation type, and this I'm going to do right now. And what I'm doing is I'm assigning a voltage source, well, which it is in reality. So if I hit the OK button, the config dialog for the voltage source pops up. And here I want to have a DC voltage, and it's a 9 volt block battery, so I say it's 9 volt. It has 9 volt. Okay, here we go. So we have now assigned the voltage, the power supply. We have assigned the simulation models for all 3 integrated circuits. So I transfer that schematic again to Felicitas PCBSim. That is, it is. And we have now a little voltage source here. I can now just simulate it by pressing the Start Simulation button, which I have done. Well, nothing has changed much. This is because we have not yet selected any trace to be outputted. I'm going to output now the output of IC2, and this looks a bit weird. Let me see. Yes, so it is a very low voltage and it's just ringing a bit back and forth, but more or less it's a constant voltage. So this is because we have not yet activated our start-stop logic. If I look at the output of the start-stop logic, it is always a very high voltage, 8.8 volts. And if I look at the schematic, if I have here 8 volts, this transistor Q2 will be switched on and it will disable the triangle generator. For that, we need the push buttons. And now the question is, how do I simulate the push buttons? There are also a number of options, but the simplest one again is that I assign again a voltage source to the push button. Here we go. But this time I say it's a pulse voltage source. And I say it has an initial voltage of 9 and an on voltage of 0, a delay of 100 microseconds. Well, rise and fall times are not really interesting. An on time of probably 2 microseconds and a period of 1 second. On the right hand side we see how this voltage source would look like. So since it has 9 volt, we will have a voltage of 0 at the beginning of the resistor, And when it goes down with that pulse, the pulse is here going up and will trigger the flip-flop. And I'm doing exactly the same here with this S2, but this time I may make it a bit simpler. I just delete this and copy S1. Here we go. And now if I open PCBSim, we have exactly the same settings as S1, and I'm just changing when it will start to 800 microsecond. Here we go. That's all. So I can again go to Felicitas PCBSim, and we see now in the tree view both switches. And I start again. And now I look at the output. Something has changed. So it's already simulating. We are now looking at the output of integrated circuit 2. Integrated circuit 2 is the second operational amplifier. And we have a nice little triangle voltage. Well, before I go into more details about how we can configure the simulation screen here, I want to stress one very important fact here. We have really only worked in the schematic. We have not done anything in the simulator at all, meaning in the main window of the simulator. But we have all done in the schematic. And the funny thing is, everything is stored in the schematic, meaning all the settings we have done are in attributes inside the schematic. I can show that. I'm open the attribute windows of one of the operational amplifiers. And here we have a number of attributes which are stemming from Felicitas PCBSim. And those attributes are defining the simulation model and the pinout for this operational amplifier. And this strategy is used through, well, almost all settings within Felicitas PCBSim. So we are really modifying the schematic. We do not save a different file or so. So everything is in the schematic. If you want to change anything and check what effect it has, you just change the schematic. For example, I can change here the capacitor to a value of probably 1 nanofarad. I hit again the export button and simulate it again and show the output, and it's now much faster. So again, I did not do anything in the simulator at all. It's all stored in the schematic. If I want to tailor now my output a bit, because it's a bit boring each time to hit the or to select the output here to be displayed, I have a very simple component in our simulation library, which is a probe. And this probe I'm adding right now here to the output. And now again, with PCBSim, I can tailor, or I can change this output. I can, for example, say it has a width of 3. It has a color of green. Oh, wrong button. Color of green. Okay. This probe does not have a layout shape, so it can remain in the schematic. I could also use a test point for that purpose. No problem at all. So I've transferred that again, and I'm simulating that again. And here we go. We have said we want to have a green thick line. We have a green thick line, and we have now the triangle output. So there are many other details which I could explain, but which would be beyond the scope of this little demonstration. Very important is what I wanted to show. We can simulate any circuit which is drawn in cuts of the eagle. It is very simple to transfer a schematic to PCBSim. It is also very simple to modify a schematic, so it is simulating. And all the changes are stored in the schematic, and the schematic can stay as it is for production, meaning all the changes we have made are meaningless for the production. So you can really just go ahead and lay out this little circuit. Okay, that's all for today. Thanks a lot, and bye for now.